Thanks. Can everybody hear me? Is the microphone working, especially in the back? Yes? Okay, great. So I was asked to provide you guys with a survey of recent results for young disks. And since I think I'm the first disk speaker of the meeting, right? Yeah, I figured I'd give you a little bit of overview of disks, put young disks in context. And I was also asked to focus on long wavelengths, specifically ALMA and the infrared, although due to my own personal biases, this is a slightly millimeter-heavy talk. But there is definitely some infrared stuff in here. As you can see, I even put an infrared picture in the beginning, right here. Okay, so first, just a quick overview of the process of star and planet formation to orient you to the ages of disks that I'm talking about here. We all know that stars and planets form in giant molecular clouds. The densest parts of those clouds collapse under the influence of gravity, and you wind up with a protostar, possibly surrounded by some kind of pseudo-disk at this stage. Maybe there's an envelope, maybe there's an outflow. This stage is very messy. This is actually not the stage I'm going to be talking about today. I'm going to be talking about when everything settles down to a pre-main sequence star surrounded by a fairly Keplerian, a very Keplerian, as I'll tell you later, disk of gas and dust. Then eventually, that primordial gas and dust dissipate, and we wind up with something that looks much more like our solar system, a main sequence star, possibly surrounded by a debris disk, possibly including planets. And you'll hear more about that later today. In fact, I think most of the rest of the talks today are about debris disks. So I'm going to focus on, oh, there was a movie. I couldn't find the movie file, sorry. It just showed graphically, I can do a little interpretive dance, collapsing cloud, spinning disk, star ignites in the center, the inner disk clears out, and you're left with these planets that coalesce out of the disk material. So that's what was in this animation. I'm going to be focusing on this stage here, the pre-main sequence star surrounded by a Keplerian disk. Just to remind us all that these are real things, I thought I would show you my favorite pictures of protoplanetary disks. These come from the Orion Nebula. So here's the constellation Orion. The Orion Nebula, of course, is down here. And if you look at the Orion Nebula with the Hubble Space Telescope, you can see that these disks actually exist around young stars. It's really beautiful. So these colors are the background nebula. The little dots of light in the middle are the young stars. And the smudgy ellipses are the shadows of the optically thick gas and dust seen in silhouette against the background nebula. All right, a little bit more about circumstellar disk evolution, just to put a few finer points on the distinction between protoplanetary and debris disks. Protoplanetary disks, like I said, are found around pre-main sequence stars. They're very, very gas-rich. About 99% of their mass is in gas. And the dust, when we look at it, seems to be more or less primordial. Maybe the dust has undergone some growth, but it does still seem to be dust that's left over from the formation of the star. By contrast, when you look at debris disks, you're looking around main sequence stars. There is very, very little gas. I used to say no gas, but we now know that that's not true. Some of the debris disks do, in fact, have a little bit of molecular gas around them. And the dust must be constantly replenished, presumably through grinding collisions of planetesimals. How do we know that? Well, you can look at the dust grains in a disk, you can calculate a lifetime for a dust grain, and you can compare it to the age of the star that you're looking at. And the lifetime of the dust grains in the disk are typically much shorter than the ages of the stars that you're looking at. So it can't be dust that has persisted since the formation of the star. It has to be dust that's been regenerated at a later time. At some point, during the transition from protoplanetary to debris disk, planets must form. By the time you get to debris disks, your stash of primordial gas is gone, so you can no longer form gas giant planets like Jupiter and Saturn. So you'd better form them before your primordial gas dissipates. So we're interested in the connection between protoplanetary disks, debris disks, and the process of planet formation that's happening within these disks and intimately tied to their evolution. So some of the questions that I want you to keep in mind today are, one, how do gas and dust interact with each other in protoplanetary disks, and what are the consequences for planet formation? Actually, I changed my second question. Now, my second question is, how does material in the disk move? And I moved my third question to how do planets interact with disk? What roles do planets play in the dissipation of the primordial gas and dust from the disk? One more background slide, and then I'll move on to showing you the actual survey of results. So when we're talking about circumstellar disk structure, just a few basics about how we learn about circumstellar disk structure. We have pretty much two main tools that we use. One is modeling of spectral energy distributions over here. This is broadband flux as a function of wavelength. These are typically log-log plots. And what you're seeing here is the short wavelength stellar emission, and then the long wavelength reprocessed disk emission. So the star is very hot. It sends out a lot of bright light. If there's a dust disk around it, it hits the dust disk, and it heats up the grains in the dust disk. Of course, they don't get as hot as the star, so they re-emit that light at longer wavelengths. So when you're seeing an SED, you've got the star over here, and the disk at longer wavelengths. And different parts of the spectral energy distribution tell you more about different parts of the disk. So the short wavelengths are primarily telling you about hot material that's very close to the star. The mid-infrared is telling you about material that goes out to roughly tens of AU from the central star, but it's optically thick still because you haven't hit this turnover yet. It's optically thick, which means you only see the surface layers of the disk. You can't see through to the midplane. And it's not until you turn over this bump and hit the long wavelength part of the disk that you can actually start to see all the way through the disk and trace the full mass distribution in the disk, which of course is one of the reasons why we love millimeter wavelengths, because they allow us to do this. Two rules of thumb that are going to come up probably multiple times in my talk today and maybe in talks later on. When you're looking at SEDs, the rule of thumb is that wavelength corresponds to distance from the star, sort of roughly as I've laid out here, although of course it's slightly more complicated than that. But this comes from two basic principles. Grains closer to the star are hotter. Hotter grains emit more at shorter wavelengths. Okay, so that's the rule of thumb. Wavelength is equal to distance from the star when you're talking about spectral energy distributions. When you're talking about images, the rule of thumb is that the wavelength of the image you're looking at roughly corresponds to the size of the dust grains that you're looking at. Why does this rule of thumb, why do you hear about this so much? Where does this come from? So at a given wavelength, only grains larger than that wavelength, really 2 pi times the size of the grain larger than the wavelength, will emit efficiently. Why is that? Well, you've got to think of grains as little antennas. Right? If the antenna is much smaller than the wavelength of light, it's not going to be an efficient emitter. You want antennas that are roughly equivalent to the size of the wavelength of light that you're trying to emit. So at a given wavelength, only grains larger than the wavelength will emit efficiently. And in these disks, there are many more small grains than large grains. When we look at the slope of the size distribution, it's pretty steep. dn dA, where n is the number of grains and a is the size of the grains, drops off as negative 3.5 or something. So it's a very steep size distribution, which means you just have a ton of surface area in the smaller grains. And so the smallest efficient emitters tend to dominate. And so you can only emit efficiently if you're larger than the wavelength that you're looking at, but the smallest emitters tend to dominate. So that means that at any given wavelength, you're dominated by grains that are about the same size as the wavelength. We have these two kind of competing ideas. So at millimeter wavelengths, we're looking primarily at millimeter-sized grains, macroscopic objects. At optical wavelengths, we're looking at micron, submicron-sized grains. And also that's important because, of course, these different sizes of grains interact differently physically with the light from the star and with each other and with the gas. Okay. So my overview of recent results. First, I'm going to spend some time talking about the interplay between gas and dust in protoplanetary disks, which is something that we've accumulated a lot of evidence for now, but it's still pretty recent, and it's fairly fundamental in how it affects our view of how dust grains move around through the disk as the disk evolves. Next, I'll talk about gas kinematics in the disk and talk about deviations from pure Keplerian rotation. Planet formation, of course, is a complicated process, and one of the things that we have to understand is how material moves around in the disk in order to understand how efficient the planet formation process is. And finally, I'll talk about more asymmetries in protoplanetary disks. This involves some asymmetries in protoplanetary disks, but specifically I'll talk about some of the asymmetries that have been revealed by ALMA in some of the recent infrared imaging, including spiral arms, radial gaps, and gap-crossing arms, that all provide hints to the interactions between the disks and the planets that are forming inside them. Okay, so starting off with the interplay between gas and dust in protoplanetary disks. We're going to be talking about radial drift and what people are calling dust traps. So here's another rule of thumb for you. Dust moves towards gas pressure maxima. The really silly example of this is, I don't know, can I borrow your pen for a second? I like this example, right? Okay, I'm going to drop this pen. Ready? It's going to move towards a gas pressure maxima. Yay, it worked. Okay, that's the silly example. Of course, you know, on the Earth, right, gravity points down, which means that the air is slightly denser towards the floor than towards the top of the building or the top of a mountain. But the same general fundamental principle works in protoplanetary disks. So why does this happen? Well, you know, we have a star, we have a dust grain. It's orbiting around the star at Keplerian velocity. But there's not only dust orbiting around the star, there's also gas. And that gas has pressure associated with it. Dust we can treat as a pressureless substance, but gas we can't. So there's more gas in the middle, less gas on the outside, typically. And therefore, there's a pressure gradient that points outwards, which means that at the position of the dust, the gas is moving at slightly sub-Keplerian speeds, right, a little bit slower than Keplerian, which means that the dust feels a headwind as it plows through the gas. So the dust, which is just plowing along at Keplerian speeds, feels a headwind because the gas is pressure supported. Of course, it doesn't have to only go in this direction. By the way, this was predicted a long time ago, Whipple, 1972. Before anybody had ever seen a protoplanetary disk, Whipple was thinking about how the gas and dust in the disk were going to move around differently. And he pointed out, you know, wherever you have a gas pressure maximum, even if it's in a ring like this in the disk, if you look down here, you see the dotted lines are the radial force on the gas. So here's our centrally peaked, well, it's not centrally peaked, but here's our pressure maximum, like the middle of the disk here. And so, of course, the gas wants to move away from the pressure maximum. That provides some support that makes it slightly sub-Keplerian. And so the motion of the dust is going to be inward. So it's going to feel this headwind, and it's going to spiral in towards the central star. But if you're moving in the other direction, away from this pressure maximum towards the central star, the radial force on the gas still wants to move away from the pressure maximum. Now it actually moves slightly super-Keplerian, and so the motion of the particle is away from the central star. So wherever your gas pressure maximum is, the dust wants to move towards that gas pressure maximum. So this is something theoretical that was predicted in 1972, but until recently we had no observational evidence for it. So what I'm going to show you today is the observational evidence for radial drift in protoplanetary disks. Actually, this is a problem. When theorists were working on this first, this is so efficient, such an efficient process, that we should basically see no millimeter-sized dust. So all of the millimeter-sized protoplanetary disk images, all of the millimeter wavelength protoplanetary disk images that I'm going to show you today, basically shouldn't be there. And you know, now we have some ideas about why we can see millimeter wavelength grains in these disks at all. But for a long time, this has been a problem, that we shouldn't be seeing these disks at all in millimeter wavelengths. Okay, so in order to understand the observational evidence for radial drift, first I wanted to start off with some history about the sizes of gas and dust disks. So this seems like a really fundamental property that we should be able to measure for a disk, right? Its size, how big is the disk? Turns out it's actually really difficult to measure for a number of reasons. So historically, here's some of the early images of protoplanetary disks at millimeter wavelengths. So Anne Dutré in 1998 and her collaborators noted that the disk looks smaller in continuum. This is the continuum here. It's kind of also in the center, but hard to see. Looks smaller in continuum than carbon monoxide, so the solid contours are the carbon monoxide orbiting around this central star. But, as they pointed out in their paper, this could have just been limited sensitivity. Gas is really optically thick, which means that you can see it really far away even when the densities are low. The densities generally decrease with distance from the central star. So even as the density gets low, because the gas is so optically thick, you can see it really far out. And with dust is optically thin pretty much all the way into the center of the star, so we just stop seeing dust sooner. So initially it was thought that the reason for this discrepancy in apparent sizes between gas and dust was simply a sensitivity issue because of the differing optical depths of gas and dust. Then Andrea Sella in 2007 wrote a paper that showed that if you fit these disks with a power law, you just take your dust, for example, and fit it with a power law, cut it off at some radius, and then you fit your gas with a power law and cut it off at some radius. If you take the CO power law and you extend the dust out as far as the CO goes, the dust should be detectable. It should have this big halo like he showed here, but it isn't. And so there seemed to be this disparity between gas and dust, and there were a couple of authors who had pointed this out. Then I wrote a paper in 2008 saying, hey, actually, if you use a realistic density structure, instead of just chopping it off at some radius, you let it taper exponentially as you go out, which is actually the predicted functional form for an evolving accretion disk, then actually we can get the size discrepancy to go away. Here's what happens if you fit the dust with a power law and try to match the gas. It really works quite poorly. But then if you fit it with this exponential taper, you can reproduce the size of both the gas and the dust using a single model. So I thought I was very clever, but then with better data, the size discrepancy came back. So we started getting even higher sensitivity, and so then we were able to look in even more detail. And so you're going to see a few plots like this. This is a plot of data from an interferometer. It's flux as a function of deprojected baseline, which basically just means how far apart were your antennas. This probes large scales where size scales are taken in a Fourier context. This just probes, large linear scales, and this probes small linear scales out here. So most of the flux you're seeing on large linear scales, and then the structure happens on these kind of intermediate scales. So anyway, this is a plot of the, also when you're looking at this, you should think of it as a plot of the Fourier transform of the radial brightness distribution in the disk. So, probably if you were plotting the flux as a function of distance from the central star in arc seconds, you would see something kind of Gaussian. And when we take the Fourier transform, we see something kind of Gaussian. So that's OK, because the Fourier transform of a Gaussian is a Gaussian with the inverse width. So that's mostly what you're seeing in these images. Anyway, I'm getting too much into the details here. The point of this is that this is dust up here, and this is gas down here. And these different lines are attempts to fit both the dust and the gas with the same models with these tapered exponential outer edges. And so this is red, yellow, green, blue, purple, red, yellow, green, blue, purple. And you can see that even the model with the tapered edge that best reproduces the data actually doesn't do a good job when you have this extremely high precision data showing you the detailed density structure of the disk. Turns out the dust disk is still too small compared to the gas. This was also shown by Itziar de Gregorio Monsalvo. She was looking at a different disk and showed that when you get really sensitive data in the really far outer parts of the disk, you can show that the gas density drops off more slowly than the dust density. And so that's telling us that something is pulling the dust to smaller radii than the gas, just as we expected in this radial drift paradigm. So there is some evidence now that the large grains are coming in to smaller radii than the gas that we see in the disk. And the other cool thing, I see the first author up here in the audience, yay. The other cool thing is that not only did we see differences in the sizes of the gas and dust disks, but now we're seeing differences in the sizes of dust disks at different wavelengths. So this is expected in the radial drift paradigm, mostly because different size grains react differently to the headwind from the gas. If your grain is really tiny, it's just going to be dragged along with the gas at sub-Keplerian speeds, and that's fine. If your dust grain is really large, it's going to feel that headwind. Well, if it's really large, it's going to totally ignore the headwind because the momentum from the gas just isn't strong enough. But if it's in the middle, like around millimeter sizes, it's going to feel the maximum headwind and drift in the fastest. So there's an expectation that there should be a difference in the size of the disk in different size dust grains, so at different wavelengths. And that is exactly what Laura showed in her paper from now a couple years ago. So here you're seeing another one of these plots of flux as a function of baseline length. And so bigger disks look narrower on this plot because we're in the Fourier domain. Smaller disks look wider on this plot. And you can see she's imaged the disk at a range of different wavelengths. And so longer wavelengths give you bigger grains. Bigger grains are smaller. The disk looks smaller in bigger grains. And smaller grains show you a bigger disk. So this is really remarkable. And then this is another way of looking at it. Here she's looking at how the grain size distribution changes as a function of disk radius, showing that basically what this is showing you is that the grain size distribution tends towards larger grains in the middle in the inner disk and smaller grains in the outer disk, which is just another way of saying the larger grains give you a smaller disk, smaller grains give you a bigger disk. So this stuff is really cool. And then also, okay, so everything that I've showed you up till now is pretty radially symmetric, or azimuthally symmetric. So these disks are all circularly symmetric. There's also some evidence for radial drift that comes from non-axisymmetries in the disk. Axisymmetries that, non-axisymmetries, so little asymmetries, blobs that are found in the disk that are in one part of the disk but don't extend in a ring around the disk. So these are called, they've been called dust traps. And so this is a beautiful picture from Nienke van der Marel's paper in 2013 showing dust size dependent non-axisymmetric structure. So what are we looking at here? Here's the central star. Here's a dust disk around it seen at ALMA wavelengths. So this is millimeter size grains. You can see there's not much going on the back side of the disk, but oh my goodness, there's a giant blob right over here. This is the carbon monoxide showing that there's a beautiful Keplerian disk rotating around the star, just as you'd expect. And this panel down here, whoops, this panel down here shows you, this is an 18.7 micron, an infrared image, showing you micron-sized dust that extends all the way around the star, just like you would expect. And then you see the millimeter dust just hanging out in this one relatively unremarkable otherwise portion of the disk. So remember I said before, we expect that different sized dust grains react differently to changes in the gas pressure. So probably there's a gas pressure maximum here. The micron-sized dust doesn't care because it just gets dragged around with the dust and stays more or less in its unperturbed density distribution, whereas the largest grains that respond the most to the radial drift caused by the differences in gas pressure get concentrated in this local gas pressure maximum. And that has the potential to be really important for planet formation because really you don't care much about what the small dust grains are doing. You care about getting all the larger dust grains into the same place so they can collect and start to form the cores of larger planets. So all of these results are showing us that radial drift really happens in disks. We now have observational evidence for it, and that it's potentially a really important mechanism for collecting the solids that go on to form the cores of young protoplanets. Are there any questions about this? This is the last thing I'm going to show you before I start moving on to the gas dynamics portion of the talk. Yes?
What are some other explanations for radial drift?
Other explanations than radial drift? Well, okay. So, so Laura's result, for example, the one that shows the different sizes as a function of wavelength, you could just say that, well, maybe it's just that grains grow faster in the inner disk than they do in the outer disk, which is also a prediction that's been made. And so these predictions are related, right? Because in the middle of the disk, the surface densities are higher, and therefore it's easier for the grains to grow larger. And so you expect larger grains in the middle of the disk. You also expect radial drift to move larger grains to the center of the disk very efficiently. And by larger, I'm saying millimeter-sized grains, not larger than millimeter-sized grains. So to some extent, that was predicted just based on the fact that we expect grain growth to happen more efficiently in the center of the disk. However, there are also papers that show that you can, so there was a nice follow-up paper by Sean Andrews and Till Bernsteel recently that I think Till was the first author, actually, Bernsteel and Andrews, that showed that that you can actually go back and connect the size discrepancies that we see in these various wavelength observation images of the disk to radial drift, and that it follows very, very closely with the predictions for radial drift. So it's probably some combination of the two, grain growth being more efficient in the middle of the disk and radial drift moving the large grains more efficiently to the center of the disk. So that's another possibility. Let's see. What else did you ask? What are some other possibilities? Well, okay. So the dust trap here, I've put it in a radial drift context. You can also think of it in a sort of hydrodynamic instability context where there are these sort of hydrodynamic vortices that form in the disks. Those are really two sides of the same coin. You can either ask yourself, okay, why is there a pressure maximum there in the first place? And that goes to the hydrodynamic simulations of disks. Or you can ask yourself, why is there this honking big millimeter-sized blob in one part of the disk? Well, it has to do with the gas pressure maximum, most likely. And then, you know, the reason why it's there, you have to ask the hydrodynamic simulations. So there are lots of different aspects to this, but I think the evidence is pretty solid now that radial drift does happen in disks, and it's tied into several of these other processes as well. Any other questions? Yeah?
Are we looking at the disk from roughly edge on?
No, we're not looking at it from roughly edge on. So it's about sort of medium inclination. I think this one is about 30 or 40 degrees inclination, which you can tell because of this ellipse up here. People will often plot the ellipse to show what do we think is the sort of projected disk major and minor axes. So this would be the like major axis and the minor axis. And the ratio of the major and minor axes is like the cosine of the inclination. So this is sort of a medium inclined disk, not very edge on.
The two circles in the middle plot is the cross toward it.
Yeah, so this is red shifted, meaning it's moving away from us, and this is blue shifted, meaning it's moving towards us. So if you imagine, I'm actually going to talk about this a little bit more in a minute, but imagine this is your face on disk, right? There's no red shift or blue shift because everything's just moving around in circles this way. So it tilts a little bit towards you. Well, which part is moving the fastest towards you? It's going to be this part over here and this part over here, right? So that's what you're seeing here. You're seeing right along the major axis of the disk, the most red shifted and most blue shifted parts of the gas. Yeah, thanks for clarifying. Any other questions before I move on? Nope. Okay, great. Gas kinematics in disks, deviation from pure Keplerian rotation. So first of all, I want to start off by taking a step back and saying disks are extremely, extremely Keplerian. I borrowed the title of this slide from something that Sean Andrews said to me once when I showed him a movie that I had made that I'm going to show you in a minute. And he said, wow, that disk is so Keplerian, it hurts. And they really, really are. So just to show you the basics of what's going on here, this relates back to the question on the previous slide. Why do we see these double-peaked lines at millimeter and infrared wavelengths in these disks? Well, it all has to do with Keplerian rotation. So I'm going to show you in this part of the talk probably a few spectra and definitely a few what we call channel maps in radio astronomy. So I want to make sure you know what you're looking at. So these channel maps. First of all, with an interferometer, we get just sort of for free, we get this beautiful three-dimensional data set. We get position, position, velocity. So at every velocity across the line where we have a channel on the disk, we get an image of what the emission at that velocity looks like. So we get position, here's position, position, velocity, and this is position, position, velocity stepping across here. So these are two different ways of looking at the data. This one shows you all 3 dimensions, this one only shows you 2. So okay, we've got to go back and imagine our rotating Keplerian disk now. This is sort of a medium inclination Keplerian disk, so it gets inclined a little bit towards you, which means that now you have a red-shifted part, a blue-shifted part, and then parts that are neither red-shifted nor blue-shifted. They're still moving perpendicular to your line of sight. So what does that look like? So the most extreme velocities are the most extremely red-shifted and blue-shifted parts of the disk, fastest-moving parts. So as we saw in the last slide, that, of course, is going to happen along the major axis. Then you also have to think about the fact that these are disks that are in Keplerian rotation, which means far from the star, things are moving slow. Close to the star, things are moving fast. So the most extreme red shifts and blue shifts are going to come from the major axis, but they're going to come from very, very close to the central star. So when you look at a map, it tends to be pretty much centered on the star, maybe a little offset to one side. Then the next easiest thing to think about is the middle of the disk, the zero velocity. This is sort of the systemic velocity here. So essentially zero velocity, and that is the part that's neither red-shifted nor blue-shifted, moving perpendicular to your line of sight. So there's a little peanut-shaped thing that happens with the front and the back of the disk, where they're essentially moving perpendicular to your line of sight, no red shift or blue shift. And then in the middle, you get sort of an intermediate thing. So here's the front and back of the disk, no red shift or blue shift. And then here's the other peak, and then here's the most extreme blue shifted. Close to the star, offset just a little, close to the star, offset just a little. Here we're seeing the front and back of the disk. This is the major axis this way, minor axis this way, and we get this nice butterfly wing Keplerian velocity pattern. Okay, so if you were to make a movie showing how this structure changes with velocity, you can do this. This is a movie. Up on the top we have data. We're stepping across the line in velocity, and this is a model of a Keplerian disk. And you can see they match extremely, extremely well. So these disks are very, very Keplerian. All you need to know is the mass of the central star, and you can do a really good job of predicting exactly how the disk is going to move in position-position velocity space. And we can see this with interferometers. This is actually sub-millimeter array data up on the top. So we've had this nice high-resolution data for a while. With ALMA, we're in a new era where we're seeing things that we never expected to see before. So up on the top here, this is a simple example. This is from some ALMA science verification data. This is TW Hydra, the closest known gas-rich disk, and therefore disproportionately well studied. And we also know too much about it, so we're finding all of these odd things in TW Hydra. One of the odd things that we found is that in the data here that you can see from ALMA, the line wings are just too bright to be Keplerian. That means that we see too much stuff. Remember, the line wings are those extreme redshifted and blue shifted parts that are coming from very close to the star. We see too much stuff that is too bright very close to the star in the line wings. So here's the fiducial Keplerian model, and this just shows you, yeah, there's really no way with a Keplerian, with a pure nice power law and temperature and density Keplerian model that we can reproduce the line wings that we're seeing. There are several different solutions. One is maybe there's some extra, maybe there's a temperature jump in the middle of the disk. I should point out that TW Hydra is a known transition disk, so we know that there's actually a gap in its dust distribution in the center of the disk, and possibly something strange going on with its gas. So that would be a reason for this discontinuity. So it could be that there's a temperature increase in the center of the disk. It could be some kind of non-Keplerian velocity, like an extreme turbulent line width or extreme infall velocities in the middle of the disk. Or it could just be that it's not one Keplerian disk, it's two. If you change the inclination, you can get higher velocities, because the more edge-on something is, the more extreme the redshifts and blue shifts will be. So you get more redshifted and blue shifted material if, say, the inner disk were more inclined than the outer disk. So these are different ways to account for these deviations from Keplerian rotation. This is a slightly later ALMA science verification data set that is incredibly beautiful, showing, I said wildly gorgeous ALMA data down here. This is another set of channel maps for the HD 163296 disk, which is one of the biggest, brightest, and therefore best studied disks. And what Catherine was able to show here is that you can't just assume circular Keplerian velocity to model this data set. You really need some of these non-Keplerian velocity effects down to the 2% to the 2 to 5% level, because they're really important for reproducing the data now that we have the extreme sensitivity and spectral resolution that's ALMA is providing. So what are these non-Keplerian effects? The vertical geometry in the disk, people had tended in the past to just say, okay, how far are you from the star radially? Well, that's going to be your velocity all up and down in the disk. Obviously, we all know that's silly. It's how far are you radially from the central star that affects your Keplerian velocity. So that's one of the effects. Pressure gradients in the gas, like I talked about previously, we know that the pressure affects the dust now, the motions of the dust. So pressure gradients in the disk are important, and you can calculate those pressure gradients if you assume that your disk is in hydrostatic equilibrium and calculate the pressure gradients from there. Self-gravity, the gas has some mass that you have to take into account. It's not just the mass from the central star that determines the velocity field, it's also the gas, which of course, this is a small effect, and we had always assumed we could neglect it previously, because of course the gas disk is going to be less than about 10% of the stellar mass. We know that to keep it stable over the long term. It has to be relatively small compared to the star. So the perturbations from some fraction of 10% of your central mass as a function of radius should be fairly small, and indeed they are. You can see they're kind of at the 2% level, but it turns out they're important. And so then when you add all of these terms together, you get deviations from Keplerian rotation on sort of the 2 to 5% level that are now really important for modeling the high quality data that we're getting from ALMA. Okay, and then third category of non-Keplerian motions in these disks is turbulence, which I've done some work measuring, and Stefan Guillotot et al. Have done some work measuring. And the basic conclusion here, I won't go into great detail, is that we can use these molecular lines in disks to measure the amount of non-thermal motions in the disk, non-thermal, non-Keplerian motions in the disk. And we've attributed that to turbulence, which is really important for planet formation theory in a number of different ways, which I won't go into now, but it affects the rate of settling of the grains in the disk. It affects how quickly planets migrate through the disk once they've formed. It affects all kinds of things about planet formation. So we're also using these molecular lines to measure turbulent motions in the disk, which is pretty remarkable. We've never been able to do that before. Okay, on to the third and final section of the talk. Since I have, 4.5 minutes, I won't pause for questions here. I'll just wait till the end of the talk. But let's talk about some more asymmetries in protoplanetary disks. And here I'm going to be talking about transition disks, which are these disks with central cavities in the dust distribution. So this is a beautiful gallery from a few years ago. Basically, the story about transition disks is that based on the spectral energy distribution, remember I told you that wavelength roughly corresponds to distance from the star when you're looking at a spectral energy distribution. So we were looking at these spectral energy distributions, and we could see that peak from the star, and we could see the peak from the dust, but there was sort of a deficit in between. And that was interpreted as missing hot stuff close to the star. Some people said, well, that sounds crazy. I don't think that's really what's happening. Maybe it's grain growth, maybe it's all of these other things. But then we took images of these disks and showed that indeed there are these giant cavities in the middle of the disk. I guess for many of you guys, especially for the young grad students in the audience, you've just gone through grad school always knowing this, and it's not really news to you, but it was pretty cool to kind of watch it unfolding in the field. Okay. So the question is, what clears cavities in transition disks? And there are several proposed mechanisms for clearing cavities in transition disks. I probably don't have time to do them all justice now, but I'll try to go through them at least quickly. Grain growth. We talked about grain growth before. Grain growth should happen more rapidly in the middle of the disk because densities are higher, grains are interacting with each other more often, so they have more opportunities to stick and grow bigger. So as your grains grow larger, the opacity at a given wavelength drops. So when you have large grains in the middle of the disk, you're not going to see them at optical and near-infrared wavelengths. And therefore, in this part of the SED, you'll get this dip just because the grains have grown basically too large for us to see them at those wavelengths. So that was one explanation for the spectral energy distributions. I think nobody really believes anymore that grain growth is the main thing that's causing these gaps in the central cavities of transition disks. There's no doubt that grain growth happens in transition disks, and Laura's work has shown that, and lots of other people's work has shown that, but it's probably not the main thing that's clearing the central cavity. Photoevaporation is an idea that's been around for a long time and keeps sticking around. So this is the idea that energetic radiation from the central star sort of starts boiling off gas from the surface of the disk. It sets up a photoevaporative wind. Why does this cause a hole, you might ask? Well, there's an accretion rate through the disk, and at some particular point in time and at some particular radius, the accretion rate through the disk is going to equal the photoevaporative wind rate. At that point, the middle of the disk gets cut off from resupply by the outer disk. The inner disk drains onto the star, and you're left with a central hole in the disk just by this energetic photoevaporation process. Nothing to do with planets. So there are lots of good things about this theory. Photoevaporation is almost certainly important for clearing out the primordial gas from these systems. However, when you look in detail at the energetics of the radiation from the star, the sizes of the gaps that are created when you measure them interferometrically, it seems like photoevaporation is probably not responsible for some of these very large cavities and the young disks that get cleared out. Another idea was binarity. Maybe there's just two stars that we can't resolve the two stars in the middle of the disk, and that's what's clearing out a hole. Of course, if you have two stars instead of one, their orbital, they will clear a chaotic zone around the two stars that are orbiting around each other, and that can clear out the middle of a disk. There have been some great surveys since this picture was taken. This is Koku Tau 4. This was sort of the poster child for binary transition disks. Koku Tau 4 was a transition disk that had this beautiful, clean gap in the middle, and we all thought it was a lovely transition disk. And then it was shown that it was just a binary with two stars in the middle. Since then, the main star-forming regions in the northern hemisphere Taurus in particular, has been surveyed for binarity in these transition disks. And we've found that most of these transition disks are not caused by binary star systems. So that leaves us with everybody's favorite explanation, which is planet-disk interaction. And a few years ago, there were a couple of great results using aperture masking interferometry that, whoops, whoa, that was loud, that showed that in the middle of these disks, we have this cavity. There was a planet, or there was a point source inside the cavity that we had imaged at millimeter wavelengths. So this is pretty exciting, and this is what people thought was happening. There have been a few results recently that I'm going to go through really quickly that have supported this result. One is azimuthal asymmetries. So on the large scale, there are these horseshoes and asymmetries in the disk that seem to resemble what we expect from hydrodynamic simulations of planet-disk interaction. I'm really going to go through these quickly. So larger gaps in dust than in gas. This is a very recent paper that came out of Caltech where you have the dust gap, and you can see the gas gap next to it. These are on similar scales, but you can really look at the visibilities and see that they cross. So the measurement of size of a gap is basically set by where it crosses 0 in these interferometric things. So this crosses at a smaller deprojected baseline than this, which means that this gap is larger than this gap. So this is something that was predicted for planet-disk interactions. Here's another example of that, overlaid on these gorgeous spiral arm structures that are likely also caused by planet-disk interaction. And finally, we've had now a couple of examples of one prediction of planets carving gaps in these transition disks is that you should see arms of material reaching across the gap. And that's what we've seen here in HCO+ in this ALMA data, and here in some infrared data from the SEED survey. There seems to be some kind of gas crossing arm over here. Okay, so to summarize, dust moves towards gas pressure maxima, solids size segregate throughout the disk, they get concentrated in dust traps. Gas and dust are not co-located. So people liked to model gas and dust in disks using the same model for a long time. Now we know we can't do that, and we have to understand the gas and dust individually on their own terms. As the data quality gets higher, it's ever more important to account for non-Keplerian gas motions. There's evidence for pressure support of the disks, turbulence, and possibly warps in some of these systems. The asymmetries, different cavity radii, and gap-crossing spiral arms are predicted features of planet-disk interactions that have now been observed. So this is additional circumstantial evidence that planets are in fact clearing the gaps in many of these transition disks. So I'll take any other questions you have. Oh, sure, yes. If everybody didn't hear the question, she was asking, okay, well, you have these asymmetries at millimeter wavelengths, but you see very different structures at different wavelengths. So here's, this is a K-band image of the disk showing spiral arms. Why don't you see those spiral arms at millimeter wavelengths? Why do you see these very different structures? There's a lot to unpack in the answer to this question. I'll say briefly, so in K-band, the disk is still optically thick, and so you're primarily seeing the surface of the disk. And so so little differences in, well, not tiny differences, but relatively small differences in temperature and density around the surface of the disk can reveal these spiral arms in the K-band, which when you get down to millimeter wavelengths, you're seeing larger grains that are responding differently to gas pressure and that are tracing more of the underlying mass distribution in the midplane of the disk. And so that's what you're seeing at these longer wavelengths, where you're seeing sort of this overall horseshoe structure in the millimeter, but it's not necessarily following the spiral arms in the disk. So there's a lot going on here. There's the different optical depths that are tracing different regions of the disk. There are things that are more sensitive to temperature and other wavelengths that are more sensitive to the underlying mass distribution. And there's also the different ways that grains of different sizes respond to gas pressure gradients in the disk. So those are some of the different categories that explain. It's really not easy to give a simple answer for why these images look so different at different wavelengths, but those are the different categories of why.